Hello everyone, and thank you so much for joining me for today's lecture. We're going to look into the statistical analysis of a clinical trial data using artificial intelligence and RStudio. Of course, you can always use artificial intelligence programs that are online. And when I was testing again for getting a script for RStudio for the statistical analysis, I would say almost all of those AI tools gave me the same script. So today I'm just going to look into any, or I would say I just randomly selected one of the artificial intelligence tools online. And we're just going to look into a very simple set of data from a clinical trial, and we're going to see how we are going to use artificial intelligence tools in order to generate a script for an optimal or a best statistical, I would say, analysis test, and then how we are going to use that script and apply that into an online RStudio application. And then we are going to look into how to interpret the results of the test that we have used. Okay, so now let's look into, I would say, the case that we are going to have. This is going to be, for example, us having a new drug that is affecting, of course, the blood pressure in our patients. So we're going to have this data set that you can see on the left. We have, again, a group A and we have group B. In each group, we do have 4 individuals, and we measured their systolic blood pressure in millimeters of mercury. So as you see, we have for patient A, 120, for second patient in group A, 118, the third patient, 122, and then 115 for the fourth patient. And then after, again, using the drug, we looked into group B. So individuals, they had 130, 125, 135, and 128, I would say, millimeters of mercury. So we would like to know if the drug is working, or maybe the drug is, which is again meant, again, to work on the blood pressure in the specific patients that we have here. They may have some chronic diseases, they may have some comorbidities as well. We are going to test to see whether this drug is also having the same effect as what we saw in other patients. So we would like to see if there is any difference in between the measurements of the blood systolic pressure before using the drug and after using the drug. As you see here, we have some tendency, and we see that for group A, again, which has not been treated or before the drug, we see that we have an average of about 118, 119 millimeters of mercury. However, in a specific set of patients with some comorbidities, we tested the drug and we found out that this drug that is used as a, I would say, antihypertensive drug in the specific patients that we have here is not working. And in contrast, this is even increasing the blood pressure. So we can see just by looking by eyes that for group B we have an average of, I would say, 128, 129 millimeters of mercury for the systolic blood pressure measurement. So now we already looked into the data, and we have questions. We would like to know if the use of this antihypertensive drug is going to be safe in our specific population with another disease condition in addition to hypertension. And we are testing to see if we give this drug to these patients, are we going to have any change, any significant change after using, again, the antihypertensive drug in our specific or special population. So for this, of course, we cannot just look into the average and then to say, okay, we think that approximately it seems that after giving this drug to our patients, we are going to have an effect, a statistically significant effect. We will need to do an inferential test. That's because we are now having a data which is quantitative data, and we can, of course, now use specific types of tests. But before even that, we may even look artificial intelligence in order to give us some, I would say, possibilities, some tests, or even the optimal test that we can use in order to compare those two sets of data. One set of data being the group A with 4 individuals and 4 blood pressure measures, and another data set where we have group B with 4 patients from a special population, and we do have 4 measurements of the systolic blood pressure. So what we should do first, of course, is to go to the artificial intelligence I would say interface, and this is where we are going to now look into, for example, u.com. Again, you can choose any artificial intelligence tool, and they're all going to give you a very similar result as well. So when we are going to look into the AI, we know that we already have our data set. The data set is as follows: A 120, A 118, A 122, A 115, and it will continue with all of the blood pressures, systolic, of course, blood pressure measures for each individual in group A, 1, 2, 3, and 4, and here for group B, 1, 2, 3, and 4 individuals. So all you need to do is just to write this query, which is written here. I just copy that, and then I'm going to go to my interface of the AI, and I'm now going to paste it. So now what you can see is that we are asking the AI tool in order to generate an R script for the R Studio. It's just the tool that we are using today to test the following variables. So we write down, of course, I would say the groups and the data. You don't need even to retype the data. If you have the table from the previous I would say slide, you can just copy and paste just this statement here instead of writing again the blood pressure, etc. here. So now that we have our R, we are having our question in the AI tool. We already asked the tool to make the R script, so I'm just going to make it run by AI, and this is going to give me again this statement, and this is exactly what I did put already in the slides here. So now that we have this script, we would like to understand it. We have here, it says group, and then there is of course some script for the R Studio. Then we see that the way that the data is now entered is this way, and the blood pressure also in another line. And then we see that the I would say the script is asking R to execute a built-in function which is called t-test, and then it's asking to perform a t-test blood pressure for each group. So as we see, the AI already gave us the statistical test as well in order to compare those two data sets before and after the treatment. So now what you need to do is to copy, of course, this print as well, of course, because we want this to display as well. We are just going to copy this script, and then we are going to now go to our online tool for R Studio. So as I already again mentioned, you go to, for example, you can go to, again, the RStudio, where you see here the web address. You're now going to copy and paste this code, okay, that are already copied, of course, but I just do it from here, okay? And then you are going to add it into the RStudio in the script section. So you're going to just paste this. Let me just do that, because sometimes it's not evident to copy and paste from one application to another one. Perfect. Now that we did copy and paste the R script generated by AI for our test, we just pasted that here in the script R space provided below. And then you can see it again, you have the groups and you have the blood pressure. These are measures of the systolic blood pressure for patients before and after the treatment. Before treatment, we have 4 patients. After treatment, we have 4 patients. And now you are going to run it. So let's go and run the script in order to get the statistical analysis and, of course, a few I would say results of the analysis. So here, as you saw, as soon as I was on script R, I did run the script, and then the system automatically did the calculations for the t-test, comparing 2 data sets before and after the treatment. And then it went automatically to our console, where it did print the results. As you see, we wanted the system to print the result. So now what happens here is that, again, after adding the code, running the code, and then to get, of course, checking that this is the right data, and then to have it, again, have the results, we are now going to understand what is exactly that the results, what we have done exactly, what are the meanings of all of these results that we get. So here, we see, of course, here the Welch 2 sample t-test. So this is the one that, the test that the artificial intelligence is, of course, I would say, recommending to us. And then it tells us that the data is about the blood pressure by group. It also then gives us the t-value, which is minus 4.17. We're going to go over the significance of these. We also have the degree of freedom, which is 5.4135, and we have the p-value of 0.007, so 7,000ths. This p-value means that those groups are different. So the systolic blood pressure before the intervention is different from after the intervention. And what we see from here is the chance of error, meaning that if we have a p-value of 0.007358, this means that these 2 data sets are different. However, the chance of error that they may not be different would be 7,000ths. Okay, or 0.07% chance that those data sets are the same. However, we have 93% chance that, or likelihood that, those 2 data sets are different. Hence, there is a significant, statistical difference in between using the drug before the treatment and after the treatment, when we are looking into the effect of the drug on the systolic blood pressure. So now let's go over in detail, of course, of the significance, or I would say the meaning of those values. So the t-value that we see here represents the difference between the means of the 2 groups relative to the variability within the groups. So a larger absolute t-value indicates a larger difference between the means. Now let's go over the degree of freedom. The degree of freedom is a measure of the amount of information available to estimate the population's parameters. So in this case, the degree of freedom is approximately 5.4135. Then we have the p-value, where it's a measure of the evidence against the nil hypothesis. Our nil hypothesis is that the drug doesn't affect in any way the blood pressure before or after the treatment. This is our nil hypothesis. Now, if you find, based on your statistical test, that your nil hypothesis is rejected, this means that there is a difference between, again, the treatment effects before the treatment and after the treatment. So the p-value represents the probability of observing a test statistics as extreme as the one calculated, assuming the nil hypothesis is true. So in this case, the p-value is 0.007358, which is 0.07%, which is very low, which is less than the conventional significance level of 0.05, standing for 5%, meaning that usually as a convention, we accept a result of the comparison in between, for example, two data sets as acceptable if we have 0.05 or 5% chance of error, since we have 95% chance of being right. So as you see, the p-value, which is 0.07%, is much lower than 0.05. And this means that there is a very high level of significance, statistical significance, when we compare those two data sets. So therefore, we can conclude that there is a strong evidence to reject the nil hypothesis and suggest that the true difference in means between group A and group B is not equal to 0. Hence, there is a difference between data sets before the treatment and after the treatment. It means that our treatment is again doing something which is a change, a real change, when compared to before the treatment. So the 95% confidence interval provides a range of values within which we can be at 95% confident that the true difference in means lies. So in this case, the confidence interval is minus 17.22 to minus 4.2725. So this is what you can see in the R console as a result of the statistical test. Now the sample estimates represent the mean values of group A and group B, which are 118.75 and 129.50. So what is the conclusion from this t-test? The conclusion is that the Welch 2 sample t-test allows us to assess whether there is a significant difference between the means of two independent groups, and for this clinical data, blood pressure for group A before treatment is different from blood pressure after treatment. Now you can easily understand that we can use also, again, the R statistics as well, R console, as a tool. Obviously, we have other more sophisticated and faster tools as well, like SPSS, like SAS, Many statisticians still now, students as well, they use Excel because Excel has also its own built-in functions. You may see SPSS or SAS being used in universities as well, in many companies as well. But at the end of the day, what happens is that we are just using the statistical models in order to conduct tests, I would say statistical analysis, in order to compare maybe variations within a group, now comparing two groups, comparing three groups, and this is why we are going to need to use different statistical models and tests. So for the end of this, I would say lecture, I would say that one of the ways, of course, is to look into, I would say, the books that we have for statistics, but using artificial intelligence also allows us to, again, do it in a faster way, making decisions that we make, however, using AI as an assistant, as an assistant that will accelerate the rate of the information that we can get, an assistant that can also propose several optimal statistical tests, and at the very end we will decide which one, of course, to use. Don't forget that in clinical research we have ICH, or International Council of Harmonization, and the website for the ICH is ich.org. And I always invite my students, of course, to go to ich.org and search for standards that we use in order to choose specific and optimal statistical tests that are used in clinical research. So again, please go to ich.org, search for standards that we use, that we have to use in clinical research in order to compare, or we say to do the statistical analysis of our clinical data. So I would like to thank you so much for joining me. And I hope that you had, you had a very good lecture, and the content is going to be useful for all of you. Thank you so much.